Okay, students, this is another video, so we're going to work through this. We're going through this fairly slowly to get all the physics and everything correctly, and provide a bit more of a foundation than what Marquez provides. But at least for this section, we're largely going to follow some of his work in Chapter 1. All right. So we're going to be talking about perfect lenses, and there's going to be two types of lenses that we talk about: a Vislago lens uh, and a Pendry lens. Okay, so Vislago had predicted a couple of really interesting things way back in when he first started when he wrote his paper that is on Moodle, by the way. And it was very interesting about how a flat slab could focus light. But it was left to Pendry many, many years later to say that it can not only focus light down to a point, but it can also do an extraordinary thing we'll find out later of capturing and reconstituting evanescent wave components of an optical beam coming from an object at the image point. So normally all these, strike that, all the evanescent beams coming from the image, the object, would be lost with lenses made out of regular materials. But Pendry came along and said that's not the case with metamaterials, that those wave components, which contain information, um, are reconstituted within the metamaterial such that when it gets to the image point, they are at the same strength as they were when they were emitted by the source, by the object. So you get all the information from the object to the image without any loss of information. And therefore, metamaterials had the promise, or the potential, potentially had the potential to create a perfect lens, one that can get around the classic diffraction limited optics. So we'll see that. Okay, so all right. So we're going to talk about negative refraction, and perfect lenses. But really, certainly, it's going to be perfect lenses we talk mostly about today. All right. So in lecture 1, we learned that light refracts on the other side of a normal vector, defining the interface for a right-handed, left-handed interface. So an interface between a right-handed material and the left-handed material, namely a metamaterial. We find that light's going to be refracted on the other side of the interface, this side of the interface, not this side, all right? Not that side, but this side, all right? To such a degree that also my k will be pointing in that direction, but my pointing vector is pointing downwards and to the left, all right? So we have k and s being in opposite directions, and we have refraction on that side, all right? So if we take theta 2 to be positive on the right side of the axis, on the right side, then we have negative thetas here. Then theta 2 is negative for left-handed material. All right. So as a homework, I'm going to have you show that concave lenses transform to convex lenses when n becomes negative, a negative index of refraction, and convex lenses become concave. All right. And so they throw that out there in the book. And it's a simple exercise, quite a bit. But it's something I'm going to assign as a homework problem. All right? And so you'll see that here probably later tonight or so. Okay, so then, so this is coming out of Vislago. We're working up to his lens. And he said, okay, normally a slab of material, regular material, glass material, with positive index of refraction is certainly not going to focus light down to a point. But if you have a metamaterial with a negative index of refraction, it will. And that's all because of the way light refracts at this interface between a regular material and a metamaterial. All right? And so you can work through the geometry, as they do in the book, and get a few relations. There's a whole bunch of similar triangles in this figure here. So you have, again, if it's not clear, we have a regular material, all right, on either side. And then we have a metamaterial in the middle. Okay. So we're going to let the slab be a thickness d in extent. And we're going to have image points A away from this interface, and and the image point B away from this interface. All right. So you can work through the triangles, and you find that similar triangles. You can find that A prime, this point right here, this distance here, over A, this distance here, is equal to B prime, this right here, over B, that right there. All right. Also, from Snell's law, you get that the magnitude of n of the slab is equal to sine 1 over sine 2, absolute values, which for the small angle formula, and that's parallaxial waves, small angles, all right, then the sines approximately are equal to tangent. That's a common assumption that we use. And then you have these relations, theta 1 over theta 2, so you can get also A prime over A is not only equal to B prime over B, but both of them are equal to N. All right, so that's going to be important. So now what we're going to do is say, okay, well, what is the total distance x from the object right here, from the object to the image? All right, well, that's going to be equal to A plus A prime plus B prime plus B. All right, well, A prime plus B prime is just the thickness of the slab D. And then we can, with this relation right here, we can substitute in for A and B in terms of A prime and B prime. Okay, they're just simply A is A prime over N magnitude, and B is B prime over N. All right, so we have a common factor of 1 over N. Bring that out, and then we have A prime plus B prime. That's equal to D again. And so we see that for these rays, the object is distance x is equal to d plus d over magnitude of n. All right. So if n is equal to minus 1, then x is equal to 2d, and this is Vizslágos's lens. All right. So meaning that these rays will be captured all right here. Okay. But only for the propagating waves. He hasn't said anything about the evanescent waves. So for that, we have to go a little bit more in detail. So now this is where we go back and we try to be consistent with Marquez's book, which I don't really like too much, because I actually think he makes he does some inconvenient stuff. But we'll muddle through it. Yeah, some of his notation is odd, but that's fine. So for the sake of ease, because you're going to be reading his book, and you want to have these notes the same, so we'll stick with his approach. So we're going to stick with his definition for positive propagating and negative propagating waves. All right. So here we have a interface along the z-axis between a normal material and a metamaterial. All right, And we're going to have waves. We're going to have an incident wave here that delivers energy to the system from the regular material side, from the left-hand side, and a beam that's taking energy away from that interface. All right. Similarly, on the metamaterial side, we have a wave that energy is propagating along the plus x direction. So we label this as the plus. But if energy is going in the positive x direction, um, generally in the positive x direction, of course it has a minus z component as well, but it's going away from the interface and in the positive x direction, then k is in the opposite direction. So the waves themselves, wave fronts are propagating towards the interface, energy is propagating away from the interface. All right, and so that's our output beam, and our input beam on this side, say, is negative. All right, because energy is going in the minus x direction, but s and k are in opposite directions, as they should be, because it's a metamaterial. All right, so hence by propagative positive, Marquez means that the waves have s in the general direction of the plus x direction, x hat direction. All right. Of course, this has a bit of a component going down as well. Of course, but we're saying that that energy is generally going in this direction as opposed to in the minus x direction. Okay. Okay, so we can go back now and use what we found in lecture 2, where we found the reflection and transmission coefficients. But let's recast that equation leading up to the final result that we'll see in Marquez's book. All right, so Marquez likes to do it this way, where he has E1 plus E1 minus as a column matrix. And so we have the E1s over here and the E2s over here. That's perfectly fine with the transfer matrix. And so then what that would be is that if you know the fields in region 2, you apply transfer matrix, and that gets you the fields in region 1. Okay? That's fine. And so normally, though, you would have the input fields here and the output fields there. And then that would be a scattering matrix instead of a transfer matrix. This is fine, but I would just generally have this as E1s and this is E2. But he has the other way around. But either way is fine, as long as you remember this and be consistent. There's some signs involved, plus and minus, that get flipped, and so it's a little hard to keep track of that. So I may if I dislike it too much as time goes on, I'm just going to rewrite the whole set of notes using the more well-accepted notation. But I'm not quite at that point yet. So, all right, transfer matrix obviously can be written like this with the different components explicitly stated. And so then we multiply that out. We get an equation for E1 plus and E1 minus as that. We know that going back to the figure, that our reflection coefficient is defined in this way as a relationship between E1 minus and E1 plus. And the transmission coefficient, T12, is this right here. All right? And you just go back to this. This is the reflected beam, and this is the transmitted beam. This right here is a transmitted, this right here is a reflected. All right? So E1 minus is a reflected. E1 minus is a reflected. And E2 plus is a transmitted. All right? So we have this, and we have these two equations. And so with all of that, we can now solve quite easily for what R and T are. So we have these from chapter 2, and so my R12 and T21 are equal to that. And so when we solve this trying to get these components, so the aim is to get these 4 components, and we know this and this, and excuse me. So we do a little bit of math, and we find that we just do some substitutions here, and we see that we get this right here for our different components: T11, T12, T21, T22. All right. Note that we are integrating within the cursive z the angle of incidence coming in and the angle of refraction coming out as 1 over cosines. So we have that within, we have the angles of incidence within this right here. Of course, this is for the TE polarization. Yeah. So that's that. That's for a single interface. The fields starting in region 2, seeing the interface, and then we hop the interface to get the fields in region 1. All right? And in the process of hopping, that mathematically, that is represented by this matrix operation. So going from region 2 to region 1, we have to do that mathematical operation. Okay, so then in that type of language, then it's easy to see how you would extend this result to multiple layers. And so we're going to now look at 2 interfaces. So we have not just region 1 and 2, with 1 being a regular material and 2 being a metamaterial, but we're also going to have region 3. That is another regular material. So that will make a slab of material. So region 3 is our regular material, region 1 is our regular material, and we're going through entirely region 2. So to do that, we start with the fields in region 3, right at the interface between region 3 and region 2. We hop that interface, and mathematically, that hopping is done by the application of this transfer matrix right here. And then we have the fields here I have this. Then we have the fields right here. So this is region 3, region 2, and region 1. And so so we have E sub 3's right there. We hop this interface. That's the application of the boundary condition, and we get the fields right there. Now we have to go and propagate back to find the fields right there. All right. That operation is done. Translating back, that operation is done right here, where the wave picks up a e to the j k2xd of phase, okay, for the positive propagating component, and negative j 2k k2xd of phase for the negatively propagating component. All right, so this adjusts the phase as we go back to that interface, and now we have the fields. Now we have the fields right here, and now we're going to hop over on this side of the interface, and that hopping operation mathematically is done by the application of this transfer matrix. So we just cascade these things. Quite easy. and that's our relationship between the fields in region 3 and the fields in region 1. All right. And this is true regardless of what K is. All right. We haven't said anything about K yet. It could be positive, it could be negative, it could be real, it can be imaginary. We haven't said anything yet. But we know from the prior lectures that K for metamaterial is going to be negative. It's going to be negative. All right. For a positive propagating beam, meaning energy that's going in the positive x direction, we'll have the wave fronts that are going in the minus x direction. That's represented by the minus K there. Okay, where was I? Okay, so that's less than 0 for left-handed material. Okay, so we're going to keep that in mind and get back to that in a bit. But first, let's solve for T and R again. Transmission coefficient and reflection coefficient. And it's quite easy to do that. Reflection coefficient is right here, E1 minus, you let that be equal to R. And our incident beam has an amplitude of 1, so you let that be 1. We have a transmitted beam here, so that will be our T, our lowercase t, and then we don't have any input beam from that right-hand side, region 3. So you let that to be 0. So when you do that, when you let this be R, this be T, this be 1, and this be 0, then you can easily then solve that equation for R and T, and you get, obviously, this. So let's consider a left-handed material slab with epsilon is -1 and mu being -1 relative. So therefore n is equal to -1. So in this case, what you find when you plug in mu and epsilons back into your impedance formulas, which are way back. Right. When I introduce, yeah, right there. Right there. You see that Z1 is equal to Z2 is equal to Z3. All right? And so you get, no, this is wrong. You don't get that. You get e to the minus j k 2x d. That's what. All right? So t is equal to that. Okay? And it's easy enough to see. When these are all equal, they cancel out with this, and you have a 2 here. You have a 2 beta 1 squared here. The 2's cancel. And you have 1 over cosine plus j sine, which is just e to the j of the argument, but that's in the denominator. You bring that up, and you get the extra minus sign. All right? And so you get the extra minus sign right there. All right. So the slab, with this, you get the slab is impedance matched. Okay, so that's extraordinary. The slab is impedance matched, meaning that you have no reflection. You have no reflection. So from a reflection point of view, and only from a reflection point of view, meaning any energy coming back, it would appear that the slab's not there. All right, it provides no impedance whatsoever to the wave. So when the wave encounters it, it just goes. All that energy can get into that slab and then get out of it on the other side. All right, so no reflection. Okay. Okay. So, okay, that's all fine. So we have a. We're going to be looking at a left-handed material or metamaterial, one in which the K2x is negative. So So we get the K2x as being negative. But we also get evanescent waves. All right? So with evanescent waves in a prior lecture, I said, okay, so you can have two conditions. You can have K be real and positive, and then your imaginary part to K will be positive as well. Or you can have a metamaterial where you have K be negative, but then your imaginary of K also has to be negative, or this right here. All right? And for evanescent waves, then your alpha is going to be this. So imaginary K is positive, is negative itself, but we define this. We pull out the negative right here, so your alpha itself is this. All right, where Kz is greater than omega squared times mu 2 epsilon 2. So then what this predicts, what this will show, is that the wave, thus as the wave propagates through the slab, the evanescent components are amplified by a factor of e to the alpha d. So the wave is growing by this factor in amplitude. Okay, so this was what really perplexed researchers, saying, well, that's really interesting. Are you breaking conservation of energy or conservation of information? And so that was a debate for many years. And then finally, folks, and Marquez says this in the book, that no, you're not, because evanescent waves don't carry information or energy. So that's sort of where the debate now still is, that it doesn't, and this is perfectly acceptable, and it's fine. So Pendry's perfect lens then. So Pendry goes even beyond what Vizlago did. So Vizlago said you can collect, you can have this slab right here in the middle, focus the light down to this image point. All right, but he didn't say anything about the evanescent waves. Pendry said, okay, after looking at what we did in the last few slides, where we looked in detail of what's going on with the evanescent waves, we're seeing that we have an amplification of the evanescent waves. So what happens is that the wave starts, an evanescent wave starts at the object, in this case. That's d over 2 away from the slab of the interface. And then it grows exponentially. It hits the interface and then it has no impedance, so all the energy gets in. But it's exponentially decreased in amplitude by a factor of e to the minus alpha d over 2. But then, as it goes through the material, it is exponentially growing to e is such that it picks up a total of e to the alpha d of additional magnitude. That's multiplied to this. All right. So we take the original e to the minus alpha d over 2 times e to the alpha d, not d over 2, but just d, to get the field strength right here at this interface. So the result is e to the plus alpha d over 2. So the field is stronger at this point than it is even at the object. That's necessary, though, because when it exits perfectly, meaning no reflection off of this interface, then it will continue, because it's in a normal material, continue to exponentially decrease in amplitude until it gets back to the image point. But to get to the image point, it travels an additional d over 2. So this amplitude right here is multiplied by e to the minus alpha d over 2. Well, e to the plus alpha d over 2 times e to the minus alpha d over 2 is just 1. And so the field comes back here with an amplitude of 1 which that was what it was, for example, when it was emitted by the object. And so we've gotten all the field strength from the evanescent waves from the object to the image via or because of this metamaterial. All right, so this is extraordinary. This is really extraordinary because this then makes a perfect lens. That's the lesson for the day. The reflections off interfaces 1 and 2 are 0, so you have no reflections. All the light gets through. Vizlago went part of the way to show that this flat slab can focus light down to a point away from the object. But Pendry went the rest of the way and said not only that, but you get all of the field components, propagating and evanescent, all of them, down to this image point. Okay. So so that was quite an achievement, and that set this sort of field afire. Because wow, if you can make a perfect lens, just think about what you could do. Especially if you can make a flat lens that's perfect. There'd be so many optical systems that would be revolutionized if we can actually make this in practice. All right. So certainly companies like Intel, IBM, ASML, photolithographic companies that make computer chips, they dumped a lot of money into R&D on this to see how you can actually make this. Because then you can make transistors that are extraordinarily small, even with regular light sources in the visible or even the UV. Because now what they have to do is, because they have to use regular lenses that have a resolution that scales with wavelength. So a resolution scales with wavelength on the numerator. So if you want smaller and smaller resolution, meaning better and better resolution, you have to go to smaller and smaller wavelengths to get around the traditional diffraction limited optics equations. All right, and so basically you can't resolve features that are probably lambda over 2 smaller in size, where lambda is the wavelength of the light you're using. And that's called traditional diffraction limited optics. That is encountered when you use regular materials for the lenses. But if you could get around that such that you don't have that equation, then that would mean that they could use the same light sources for the photolithographic systems, which are the things used to draw the computer chips, draw the transistors. Then that's great. You only have to swap out those lenses and you're good to go for however small computer transistors you want to make. Instead of spending the billions upon billions of dollars developing new lithography systems that have smaller and smaller wavelength of light. Those are extraordinarily expensive to develop, and now they're down to X-ray lithography. And that has turned into quite a mess. How do you actually produce X-rays in such a system? All right, and so that proved to be difficult. Anyways, they have actually succeeded in doing it, but it is a quite bizarre way in which they produce X-rays in those systems, and it's not ideal by any means, but it does the job. So, okay, what's held this up? And this, I mean, the metamaterial lens. Well, two things that have held up a lot of amazing metamaterial applications, and that is bandwidth and loss, and additionally fabrication complexity. So as we'll see in all metamaterials, you invariably have loss such that even though you may not have a lot of reflection here at the two interfaces, you have a general loss of energy as the beam goes through the material. And that's just due to the fact that to make negative epsilons, negative mu's, we have to use, in the past, a lot of metallic structures. And within metals, you always have non-idealities where the optical energy is transformed to heat and heating up the metal, scattering off of irregularities and all sorts of other things. So you have a lot of loss with the materials we can make right now. But that will advance. We will develop new ways of making these materials. We will be able to make the metamaterials probably through some chemical ways, such that we find various molecules or supermolecules that we can engineer in the negative epsilon, negative mu, and not use the CMOS fabrication techniques to have to make the metamaterials, but use all chemical ways. Bandwidth is another thing. So sure, it works at one wavelength, but if you go slightly off that wavelength, then you find that that it doesn't exhibit the same metamaterial properties. So optical loss, small bandwidth are two big problems, and then also how do you actually make some of these structures? So that will be, those are ever-present challenges in the field of metamaterials. But the physics is there, meaning that once we figure out a way to reliably and conveniently make high-quality metamaterials, the physics allows us to make these perfect lenses. So really extraordinary. So that's the lesson for the day, and that's a lot to chew on. So I see we're only at 37 minutes, so it's not a long lecture. But in terms of what has been presented before you, it is extraordinary. So something where you take the rest of the time and you really think about this and go through chapter 1 and go through the notes and say, so we've learned that for the last 200 years or however long, when we had thought that we were always limited to had diffraction limited optics, that lenses can't be perfect. So today you've learned that that's not necessarily true. We can make this perfect lens. So really neat. Okay, great. You'll see a homework here shortly.